You all to the Google Open Source Developer Speaker Series. Our speaker tonight is Amit Singh. I've been fortunate enough to know Amit Singh for about 6 or 7 years now, and to work with him for most of that time, and to be around to see all the wonderful work that he's done, from operating system virtualization work that actually we worked on together, to his exploration of Mac OS X and the stuff that he's been putting out for OS X, as well as his book, Mac OS X Internals. And recently, I had the pleasure to watch him work on an additional project, which is called MacFuse, which is what he'll be talking about tonight. And it's kind of fun to watch him at work, because sometimes he goes in this mode where basically he does not need sleep, and he can just work for weeks and weeks at a time without sleeping, and it's basically very interesting. So I'm hoping you get a feel for that tonight, as he basically tells you in person about MacFuse.
Well, thank you. Ted's very kind. And thank you all for being here tonight. So this would be this can be a pretty free-form talk, which means we can adapt pretty dynamically based on what the audience is. I'm not very sure what the audience is here, actually. So how many people here would want So we will talk about MacFuse and how it works and how it was done and so on and so forth. But how many people don't even know what it is, or would like me to give a very, very brief elevator pitch thing on what it is? OK. So I'm not sure if this will be helpful, but you can think of it as a set of building blocks, programming tools, libraries, that you, as a developer, as a regular OS X developer, can use to take any information, whether that information is on your disk, whether it's on a remote machine, or whether it's not even anywhere, you're cooking it up in your program, and put that information in the forms of files and folders. So make it look like it's a file system. And why you would want to do that, what are the benefits of it, what kind of things can be done with this technique, we'll talk about that. But that's the gist of it. And also curious, how many people are here because they think they would like to use it or might want to use it in their own projects or products? OK. So sounds like we could be a little bit technical here. So I'm sure people would have noticed the scrolling thing that was running for a while. That was actually an actual Unix system from the early 70s. And it was running on one of these. So this is it's a Nintendo Game Boy. So it was running on a PDP-11 emulator, running on a Game Boy emulator, running on Mac OS X. Well, it was running like that, well, because I can't actually put this there. So, yeah, what's the point of that? Well, I'd like to start with a comparison of what used to be, let's say, at the dawn of the modern operating system's age, which, well, given how successful Unix has been, let's say, around the time before Unix was born, to what we have today, and in the context being Mac OS X. And I do apologize for this, because I personally find it very valuable to look back upon things, look at the history of how things are, how did they come to be what they are today, what paths they took, how many times they were reinvented. So most of my writings and talks do have like a reasonable dose of history. So if that's not your thing, sorry, but I can't help it. So if you look at these aspects of pretty much the first version of Unix and compare it with Mac OS X, so you will see that lots of things have blown up a lot. And that's to be expected, especially like You write the same one-line program, it just takes 13 times more space now. Another thing is that since we were talking about file systems, so Unix just had one file system and it was fine. It was good enough for the people who use it. And depending on how you count it, Mac OS X has like 15. Certainly more than a dozen, but 15 is a good number. So it would be helpful to see like how we got from 1 to 15 and why 15 are not enough and why do you want more. So given that, let's go back a little bit before there was Unix, actually. So there was this operating system called Multics. People wanted a decent operating system. People wanted computers to be usable by everybody. So, but the one aspect, and many aspects of modern OSs, including OS X, can be traced back to this one system. In particular, the file system. So in the mid-'60s, there's a paper published, and they talked about what a file system should be, and they talked about a hierarchy of files and folders and file permissions and open files and closed files and backup mechanisms and file sharing and this and that. So pretty much what we have today, but this was back in the '60s. And then, as the history is well known, Multics led to Unix. And so how did file systems work in Unix? There was only one file system, so it's very simple. The operating system knows this is the file system, that knowledge is really hard-coded into the operating system. So if a program wants to read and write, make system calls, they go into the kernel, the system calls know about the file system, and that's what you have. It's pretty simple. But this was never going to be enough because people have different needs. The internet happened. So you need to be able to read from across the network and do this and do that. So people wanted to add more file systems. So how do you do that? Well, just make a kind of a switch statement and have some type identifier and see if it's this one or that one. And you can kind of expand the code and accommodate it in the same framework. Now, what happens if you add more? So it becomes like this. And so I shouldn't have to tell you really why this picture is not good. I mean, the things at the bottom are sharing a lot of code. The switch thing is really complex, and you really need to recompile the kernel, recompile the operating system for this to work. And so this is before there were kernel modules and things like that. So this thing is really not maintainable. And how far can you go with this? So a better way to solve this problem was needed. So the solution was something like this, that you don't really want the top layers to change because a lot of software has been written already. And that's part of the reason why Unix was successful, because it's very easy to use, easy to program for, it's reasonably standardized, not standardized, but reasonably similar. So we have two file systems here, two file systems actually taken from Mac OS X. And when I say file system, it's a very vague, overloaded term, but for the topic of this, for the purposes of this discussion, let's say a file system is just a set of operations and some objects. So you're creating files and directories, reading them, removing them, this and that. So it's better that the top layer is not aware of every single type that you introduce. So it's kind of obvious that so Sun Microsystems came up with a solution that instead of things being specific, the top layer should just deal with only one type of things. So instead of these HFS plus files and folders and UFS files and folders, let there only be one kind of files and folders, and let's call them virtual nodes or vnodes. And instead of specific operation types, let's just have one kind of operations called virtual node operations or vnops. So this really is saying that, kind of object-oriented, we are saying that we have a concept and then we have specific implementations of it. So pretty obvious way to do it. And this was known as the vnode VFS concept. And so this thing came out in 1984, and it was successful enough that OS X uses it still. Pretty much most Unix-like OSs use it. It's the same idea. So that's good to know. but 84 was a long time ago. What happened? There were lots of other developments in distributed file systems, and even vNode VFS was not the only thing. Companies like AT&T and DEC, they had essentially the same ideas and essentially the same solution independently done. But for various reasons we will not and shouldn't go into here, there's no time, vNode VFS prevailed, and that remains the way of doing things even now. So, okay. So let's think of some OS vendors. Now, given that we have vNode VFS and that's the way you write new file systems, it's reasonable to expect that OS vendors, let's say Apple, Microsoft, they would use something like this to create new file systems. When Apple introduces a new file system, that's what they use. Pretty reasonable thing, okay? Let us compare, let us take some common file systems that Apple has, and let's compare how complex they are relatively. Now complexity is a pretty complex topic, and lines of code may not be the best metric because sometimes you remove lines of code and it becomes more complex. So, but given that all of these should be using the same underlying interface, lines of code is not that bad, and this is the best we can do in this talk anyway. So as we see, HFS Plus, which is the primary file system and Apple's main thing, it's quite complex. It's actually something like 10% of all BSD code in the kernel. And as we go to the right, we see that WebDAV, which is the file system that you use for mounting your iDisk, that's pretty small. And whatever happened to FTP? It's actually 0, but I wanted to kind of make it look like it's, so it's this 1 pixel wide line, a high line. So what's going on? Well, what's going on is that this thing said lines of kernel code. FTP has no lines of kernel code in the macOS 10 kernel. So how does the file system work? It's something like this. So NFS is a pretty old, long-standing protocol. macOS 10 supports NFS. What if we took code for an NFS server and just ran it locally on our machine, and we modified it so that instead of serving files that it normally would, it would actually talk to an FTP server and it would serve that content instead. And then OS 10 knows how to mount an NFS share. So that's essentially what it does. So the FTP code for the FTP file system actually lives in user space. So that's how they do it. And you also remember that the WebDAV thing was pretty small too. So why is that so small? Well, the reason for that is that it's somewhat similar logic, except they're not using NFS. They're using a custom protocol. And you put a small in-kernel file system, which is essentially a shim, that forwards all file system calls to user space. And then you can have an arbitrary complex WebDAV daemon that talks HTTP to the server. And you can put whatever logic you want. You can put UI on top of that and do whatever you feel like. So, but conceptually, it's actually the same picture, isn't it? Now, let me sort of jump forward to MacFuse, or strictly speaking, the Fuse idea. What is Fuse? This is Fuse. You put something in the kernel, you provide a library, and then it talks to this thing in the kernel through some mechanism here, a device. Now again, it is pretty similar to what I showed you in the previous two instances. So what is the difference? And why do we want to do this? Well, one way to think of this is that you can do this. So in the WebDAV case, the protocol they were using to talk to the kernel is kind of ad hoc. It's done only for WebDAV. Now, one could say that we can take the WebDAV code and extend it and modify it and all, but try looking at that code. It's not trivial. One could keep using NFS, modifying NFS to do that, but if you've ever worked with NFS, you will know that that's not trivial either. So LibFuse is comparatively much, much easier. So what we are doing here is, just as VFS, vnode VFS, that concept solved the problem of accommodating multiple file systems in the kernel, what's semantically happening is that we are pushing VFS up into user space. But there's a critical difference. I said that the VFS is very complex. Actually, I didn't say that, but it is very complex. That's one reason why you don't want to program a file system in the kernel, simply because the sheer number of things you have to do, you have to interact with so many subsystems, you have to interact with virtual memory, you have to do buffer caching, you have to do all kinds of reference counts and locking and this and that. It is sheer torture. And there's no scope for error. So you don't want to do that. So logical thing, or logical next step, kind of push it into user space, and then we all know how to program in user space. It's much easier. There's a vast number of tools available, debuggers available, libraries available. You can do whatever you want. So that is sort of the idea. But when I say push VFS into user space, I don't mean provide the same API. You don't want to be using that API. The API is very low level. So you don't want to be dealing with those virtual nodes or vnodes or inodes or that ref counts and whatever. You need to be doing something really, really simple. And that is the motivation here. So a good idea. The other thing it does is that it generalizes this thing in user space, but at the same time, it standardizes. Because the other two cases we saw, for FTP, we use NFS. For WebDAV, we use this ad hoc protocol. For something else, we might use something else. But we are solving the same problem again and again. And if you want to write 100 file systems, then this is not the way to solve it. So the other thing this is doing is it's giving you a standard API. Use this, write your file system, it'll work just the same. So sounds like an obvious idea. But why are we talking about it now? We said the vnode VFS thing came out in 1984. So did nobody do it? Did nobody think of it before? Well, they did, many, many times. And I could talk about all of these, but this would take a few talks. So essentially the exact same thing, and arguably in some cases even better ideas have been done, implemented before in academia, even as complete operating systems. But where are they? I mean, they didn't succeed for one reason or another. We're not using them today. But that's another story. And one thing is Unix was just too relentlessly successful. So being better is not the problem, or doesn't solve anything. You're not Unix. So, but maybe we can do, we need a little more justification as to, okay, then why is Fuse better? What did Fuse do differently? I think several things. So Fuse started as a file system shim in 1998. And the very first version came out, actually it came out in 98, but then it was rechristened as Fuse in 2001. And it's been developed a lot since then on Linux. So I think Linux historically has had a very active system-level programmer and user community. So I think Linux was the right system to house it and for it to be released that way. So it got lots of people implemented. Another thing that happened was that the author of the original Fuse, he implemented what I think was the killer app for this. He implemented the SSH file system. And everybody just wanted it. Everybody needed it. And so everybody just adopted Fuse. And once they had it, they probably thought, hey, this is pretty easy. Let's just develop for it. Another thing that happened over time was, so Fuse is now in the official Linux kernel tree. It's part of the Linux kernel. So it's been like it's official. It's been blessed. The other thing that happened was that people added lots of language bindings. So you're not just limited to programming in C or C++. If Perl is your thing, or Python, or Java, or Ruby, or whatever you have, just program in that. The point is there's a C library. So you can morph the C library. You can put any other language binding wrapper on top of it. just as you can with other things. So you can write a file system for crying out loud in whatever language you want, and this was something unimaginable. So we have lots of hobbyist programmers who are writing all kinds of file systems, and just as they would write, a web page JavaScript thing. So pretty neat, because it's quite resilient. If you have a problem, if you make a mistake, you're not going to take down your system, or at least that's the idea. So Fuse is successful. I told you so, but maybe we should visualize it a little bit. I say Fuse is successful because it has a lot of file systems for it. People have written a lot. Here are a few. So at this time, there are at least 110 or 120 file systems that people have written for it. Now, not all of these might be useful for everybody, but I think everyone will find at least a few that they fancy, or a few that, why didn't I think of this idea? This is kind of nice. So this kind of is the background. Now, what exactly is MacFuse, and how does MacFuse fit into the picture? So let me tell you a story. I started using the Mac in 2003, and I'd been an OS programmer, and I'd worked on lots of other systems, but not the Mac. But there's only so much you can do. Like, I clicked on everything that there was to click on, and okay, it's not really Linux that I can keep recompiling the kernel every day and configure the hell out of it. So what else is there to do? So started looking into like how the operating system works, and how the kernel works, and one thing I realized was that they didn't have a proc file system. They didn't have a process file system. It's a very Unixy thing. It's been on most Unix systems, or Unix-like systems. So I thought, okay, let me maybe this is a good thing. Maybe let me write a proc file system for Mac OS X. And so I don't really like programming. And no, I really don't. I really like the end result, and I want the end result to be high quality, but I would do anything to reduce the programming or find like the fastest or shortest way possible. I just don't like programming. Don't hold it against me. Well, maybe that's why I'm a manager now. So I looked at some ways of, let's see what can be done here, which would be really cheap and wouldn't require a lot of programming. So lots of people think that OS X is essentially BSD or essentially FreeBSD. Well, it's not. But that's a whole other story. So it's not FreeBSD, but it has FreeBSD heritage. So at least it's closer to BSD than, let's say, Windows or Linux. So BSD has a proc file system. So I started looking at the BSD proc file system, and a lot of it was generic, as in it was dealing with strings and strings management, because proc is virtual, right? So you're creating a namespace, which is just a hierarchy of files and folders, which are basically strings. And then you're cooking up some content. So it had a lot of BSD kernel tie-ups, but it was largely, not largely, but still, a lot of it was generic. So I thought, let me rip it out and provide what's missing on the OS X side, and we'll have a proc FS going in no time. So I spent about a couple of weeks on it, and it did mount after that. But if you're programming the kernel, or if you've written any file systems, what's the first thing that happens when you mount a file system for the first time? You have a kernel panic. So I had a kernel panic. And OS X needs 2 machines to debug, because there's no built-in debugger that works like in Solaris or some other things. So I only had 2 Macs at that time, and around the same hour as I had the kernel panic, one of the Macs died. So I was new to Apple service. I was new to Apple, and I was new to how Apple handles service. So I took it to the Apple store. I'm very, very impatient. Hey, I'm in the middle of a kernel panic here. I'm writing a file system, and I have to get it fixed while I have my interest in this thing. Otherwise, I'll never do it. And the Apple genius is like, yeah, did you try resetting the PRAM? I'm like, dude, the motherboard is fried. It's dead. You need to fix it. So they told me it'll be 3 days. Okay. little did I know that you need to back your disk up. So the motherboard indeed died, and or maybe it was the VGA cable. It was one of those two things. So they took 10 days, 15 days. I kept going to the Apple store every day. They must have thought I really like iPods or something. They didn't fix it. It took a long time. Then they gave it back to me. And then the hard drive was busted. Like, not just erased, it was busted. So they broke it. And my code's gone too. So I took it back. So it took me like 45 days total to get the machine back. And I never went back to ProcFS. It was painful enough the first time, so yeah, forget it. So that's, why did I tell you that? Maybe it has a meaning. So one fine day, a few months after I joined Google, so I was talking to my office mate, and WWDC had just ended, and we were just talking about what do we need on OS X that it doesn't have. It's really nice to have. I had thought of two things previously. One was dtrace, the tool from Sun for debugging and stuff. And the other was something like Fuse, something that makes file system writing easier. And at WWDC, Apple announced that they've brought dtrace to macOS X, so that problem's taken care of. And I'd actually asked one of their engineers over there, can you tell me, are you working on Fuse or something like that? Because if you are, please do not make me waste my time again. I can't tell you why, but so they said, no, we don't think so. So it looked like Fuse would be a nice thing to bring to the Mac. And Google is kind of really nice with the 20% thing and all. So I didn't really know how genuine that thing is, and because I worked in all kinds of places. So I wanted to take up Google on that offer that, sure, 20% time, why not? So OK, I thought this is a good idea, let's do it. And then I wanted to, it's always easier in hindsight to put down your goals. These were the goals, so you can't really tell if I actually had these goals, but I'm saying I had these goals. So the goals were, whether you're a user or a programmer, if you want to write a file system or use a file system, it should be easy. Like in the case of ProcFS, I should be able to write a file system on impulse. If I want to write one, I should be able to write one. It shouldn't take like 5 months of preparatory work just to write a file system. That's one thing. The other thing is that there are things missing on macOS X that would be really nice to have. SSHFS is one thing. NTFS that you can write to is one thing. FTP that you can write to is one thing. For some things like FTP and SSH, sure, you can find products that do that. But it's not transparent, seamless support. You do because that only happens in the product. It's not like any application can make use of it. It's not a real file system. So it'd be really nice to have a few more file systems on OS X, whatever one needs. The other thing is I'm quite impressed, or I have been quite impressed with the kind of products the Mac developer community creates. It's like so much attention to detail and very different from, so it's good and bad. I'll not talk about the bad. But the good part is that they're a joy to see and use and look forward to new ones. So if we give people, if I did something that gave developers, innovative developers, a really powerful tool, it's pretty exciting to think, what would they do with it? So that was one of the things. And I talked about cheapness and not wanting to do programming and whatnot. So I just showed you that Fuse had a lot of file systems. So if we stuck to the same API or pretty much the same API, then we should be able to use most of them. So that's another thing. And another goal, which is not just for MacFuse, it's in general that I personally have, is that if something that solves 95% of the problem or 95% of the people's problem versus something that solves everybody's problem but takes 10 times more work. So I usually try to draw that line, and if there are compromises to be made, that if I did that, I'd make that one guy in Iceland happy. Then if it took me another 6 months, then I would rather release it without making the Icelandic guy happy and just talk to the guy offline and tell him that it's not for you. I have lots of Icelandic friends, that's why it popped up. And the other thing is that when I say that give developers powerful tools, the other thing is that you shouldn't have to be a research scientist, or you shouldn't have to know like file system theory inside out. You shouldn't have to recompile your kernel. You shouldn't have to replace core system components. You shouldn't have to lose your data or have a kernel panic. So when I say powerful tools, it also means very convenient tools that don't do any of that. And of course, not limited to any programming language. You use whatever you want to use. So these were the goals. And now that we know what the goals were, so how does one start an undertaking like this? Because it's quite huge. Like the actual work involved is a lot. So I have a few techniques for doing something like this. So what I often do, and so here's an example. So I had a project like this. Well, not exactly like this, but I had a pretty big project for the last couple of years that also needed a lot of analysis and work and programming and this and that. So here's a picture, a war picture from the project. So on the right, we have a Power Mac. And on the left, we have a stack of papers which contain the notes that I made for when I wrote the macOS 10 book, and also the papers that I read on the subject. So essentially, that's the research work. And the condensed result of this work is in this tiny book, relatively speaking. So that's kind of the approach I use, that one could say that 1% inspiration and 60% preparation and 39% perspiration. But preparation is huge, and it especially helps in that short-circuiting and avoiding. So this is, I think, so we have lots of these giant plotter printers here at Google. So I went to one of those and I got a few sheets like these. And this is actually the overflow sheet. I can't find the original. And what I decided was that the obvious thing to do here is to take whatever Fuse implementations are out there, Linux and FreeBSD, and kind of create a software map of the thing. Because if you don't even understand what you're trying to implement, because it's not a published standard, so there's no published specification. So it's just some complex piece of software. You got to figure it out. You have an intuitive idea of how it works, but first you need to know how it works, and then you need to map it to your platform. So with that, so I guess I can talk about like a block diagram of what MacFuse is, and then how I went about filling those pieces in. So here's a very simplified picture of what MacFuse can be thought of as. So the simplest delineation is that there's some stuff in user space, and then there's stuff in the kernel. So the stuff in the kernel at the bottom, and the stuff in the kernel really is a complete file system. So when you're writing something like this, well, an obvious goal is that I really want to have something mounting first. Maybe I just want like a trivial hello world kind of thing mounting. Now, but the catch is that whether you're mounting hello world or whether you're like actually doing a lot of other stuff, most of the requirements are pretty much the same. You actually need to have a lot of this stuff in place for anything to work, even if it's a hello world thing. Because this is not something, this is a file system, so the kernel doesn't know that your intentions are not so evil and all you're trying to do is just write a file system. So it won't let you get away with anything incomplete. You still need to put in a lot of work. So with that, number one is essentially the file system, the operations on this file system, deleting, creating, reading a directory, renaming. There's actually a lot of these. It's like 50 or so. So I decided to implement almost all of them, because I knew that whenever I have something more complex going on, I will need more of these. So it's just better to have a more solid foundation to begin with. So I just spent some time, probably about 10 days or so, just writing the thing at the bottom. So when this was done, what we have is a file system that does nothing, but it has all the operations. They're pretty much stubbed out. And then you need to have this thing talking to user space. So you need a communication channel. So macOS 10 is rich in that you can do this multiple ways. You can do this like through the IO kit, or you can do it in a BSD-style fashion. So one of the code bases I was using for reference, which is the FreeBSD implementation of Fuse, it used the Unix-style /dev device communication. Basically, you open a device and you read and write to it. So I wanted to save time, so I decided to use this code as a guideline and to save some time that way, even though in the case of macOS 10, there may be cleaner ways to do it, but hey, that's the tried and trusted way. So the BSD implementation was especially handy. And then I started to look at the user level stuff, because once this thing is done, so we have a file system, it's got everything in there, all the operations are there, and it knows how to talk to something in user space, but we have nothing in user space yet. So libfuse, that's the Fuse library. That comes from Linux. One would assume that since it's a user space library, it's quite portable. It is actually reasonably portable. It's one of my pet peeves when people say porting. What do they actually mean? So my definition of porting is you take a code base, it's really portable because it just uses C and the standard C headers or something pretty common. You take it to some other machine, you compile it. Probably it'll just work. If it doesn't, oh, this doesn't have this header, you make some few changes and it works. Now, if you take next step and you change it into macOS 10, no, or even worse, is macOS 10 a port of BSD? No, but I wouldn't be surprised if people call it that. So the kernel part is not a port. It can be ported. There's just too many differences. But I really expected the user space part to be portable. And actually, it was for the most part. But macOS 10 can be quite sneaky. There are things that work a certain way, or certain way being what's in the POSIX standard on Linux. They don't work the same way on macOS 10. So things like if you want POSIX semaphores, they may not work the same way. Sure, you can have mock semaphores instead, but you have to change them. You have to change the calls and do whatever. pthreads, pretty common programming interface. pthreads may not work exactly the same way on macOS 10 as you might expect, especially if you're canceling and stuff. So there were a few hiccups like this with the library, but after changing this, it kind of just worked, meaning I could compile it at least. And then mounting works differently on OS 10, so you can use the mount program, which if you're calling the finder or something, somebody eventually has to call this utility called mount, or the system called mount, to mount a file system. Now that's different on OS 10 versus Linux, and actually reasonably different from FreeBSD 2. So those are a couple of tools. LoadFuseFS is going to load the file system kernel extension. MountFuseFS is going to mount it. So once I had most of these things done, and the thing is that there's a 10-day period that I don't remember, because that's one of the things that Ted mentioned. I think I was in the zombie mode. So I know I was trying to get it to work. I don't really remember the timeline, but suffice it to say that it did work after that. Like I could mount the hello thing, and then after a few more days I could mount the SSH thing, and like, all right, this is fine, this will work. So, then we released this at, oh yeah, and so once I did this, so remember, I'm trying to do this as a 20% thing, but then 20% is only so much, so it becomes a lot. And then, but what to do with it? So one of my goals, I didn't actually say it in my goals, but I really wanted this thing to be open source. Simply because I think that's the right way to do it. I'm not saying it as an open source zealot, but I think I looked at lots of the open source stuff while I did this. For some of this stuff, I reused some of the open source stuff. So even if the license permits me not to open source it, I personally feel that it's just best to share it. And if somebody else wants to go through the pain, at least they should either not go through it or they have like a guiding thing. So it was surprisingly easy at Google to open source it. I just asked my boss that, hey, so this is the thing we have. And I was expecting a very bureaucratic, like some meetings will be called and the code audit will be done and I'll be asked how many licenses you have and where did this code come from and this and that. They said, sure. Like, is that it? Yeah. You're kidding me, no. Okay, so great. So Google was very, very helpful and supportive. So all it took was just telling my boss that I need to open source it. And again, I'll use lines of code as some sort of progress indicator. Again, it's kind of sometimes progress is when you remove lines of code. And in fact, often removing is good. But this is kind of the timeline. Right now we are version 0.3. Versioning is another issue, like why 0.3 and why not 1.3? There's another thing with open source projects that they remain at like sub-decimal versions for their lifetime, but let's talk about that some other time. So we released it around Macworld, at Macworld in January. And since then, the blue thing is the user space code. So you'll see that the user space code hasn't really changed much. But the kernel space code has, keeps getting bigger and bigger. Although at least the slope is getting, the rate is slowing down at least. So now let's go back to the other slide we had. And so with this, where does MacFuse fit? So like I said, it's a kernel file system. Well, it's kind of like this big. And since we talked about ancient Unix in the beginning, so these are the file system sizes. This is the size of the MacFuse file system. This is the size of the entire Unix kernel in 1974. The whole operating system. So times change. Anyway, so since we are, okay, so this tells you that, the kernel part is this much, but what does it do for you as a developer? So do you save anything? Do you save effort? I talked about all those goals and promises. So, okay, let's see, if you were to write a file system in the kernel, if you did decide to go through all that pain and suffering and lose your data possibly and write a file system that just did hello world. The file system has just one file, contains hello world. So this would be the size of it. Well, it has to be relative to something. And then you did the same thing in MacFuse. What would be the size of it? So here's a comparison. So that would be the size of it. That looks pretty good, huh? Now, but hello world is trivial. But like I said, one should be able to write file systems impulsively. Let's say that you have a product or a project where, for whatever reason, you need a 128 terabyte file. You're writing a backup software tool or something, and you want to see how it behaves if it encountered a 128 terabyte file. Sure, you can try creating one. It'll take a long time and a lot of space. But with MacFuse, so what you could do is that you could quickly whip up out a file system that just has one file. And since you are writing the file system, you can just claim that the size of the file is 128 terabytes. Now, what happens when the backup software, whatever you're testing, wants to read the file? Well, the way operating systems work and the way the kernel works is, in your read routine implementation, in the callback that you will get when somebody tries to read it, you can just say return 0, which means you have no data for this file. And what the kernel will then do, or MacFuse will then do, is that it will zero fill the data, because the file system failed to provide the data. The data has to come from somewhere, so you'll just get an endless stream of bytes coming from the kernel without you doing anything. And in fact, the entire code for such a file system can be represented on the screen. It's kind of small. I had to make it fit, but that is it. You do that, and you have a 128 terabyte file. Now, so Still, there's Fuse for BSD, there's MacFuse. So hopefully it is clear, and if it's not, let me spell it out again, that there's a specification or a protocol or an understanding or an API called Fuse, which is these are the messages, or this is the communication you will have between user and kernel. And each OS is free to implement however they want it. Now, MacFuse tried to stay very close to the Fuse API simply because it's good compatibility-wise. We want to reuse all the file systems. But the platform is completely different. Mac OS X is not Linux. So there's got to be some differences. And different challenges, like different challenges for me as an implementer of this thing. So on the good side, we can also have features that are specific to OS X and maybe Linux Fuse doesn't have. So what are some of those things? Let me talk about some of these challenges. So one of the big challenges is that OS X is a closed system. Wait, Darwin is open source. Well, I don't really mean that I can see the source. Sure, I can see the source, but the way the system is set up, the way the user base is, the way people's expectations are, let's say that the kernel doesn't do something right, or doesn't do something that's okay for the built-in file systems, but it's not okay for new file systems, or not okay for MacFuse. And I know that if you change that one line there, it's all good. It'll work for both. But can I change that one line? No. If I talk to Apple, I don't know how, but let's say I send somebody an email. Dear Steve, can you please change this? You think that's going to happen? No. So, which means I have to figure it out somehow. I have to work around it. I have to do something. A very, very good example of this is that when something opens, so let's say you wrote a Fuse file system. It works with MacFuse, it works with Linux Fuse. And in your file systems, you want to be able to receive an open callback when anybody opens a file in the kernel. So great. That's how Fuse works. Fuse, whenever the open system call is called, Fuse calls out to user space and tells your file system that, hey, there's an open call, please handle it. Now, the Fuse API also has this thing called per open context. So every open, you can decide to like stash some context information, your own data, somewhere. And then in close, you can remove it, deallocate it. But for this to work, you must receive all opens and closes. Otherwise, there's going to be a mismatch. Now, this is fine on Linux because the Linux kernel is very file-centric. The file system in the kernel actually knows that if you're opening the same file 10 times, you're receiving these open calls, and it knows that this is this file descriptor, this is this file descriptor. The same way on FreeBSD, even though it's vnode VFS, the file descriptor is actually passed to the file system. So you can use the file descriptor as the distinguishing discriminant and figure out what to do. In OS X, MacFuse will receive every open, but you won't know which file descriptor it's for. So I will receive every open, and I'll receive every close, but I can't match the closes to the opens because I was not given any further information as to which instance of this file open was this, which means you can't do this. You can't forward every call to user space because you won't know which one to release. Now, what is a pragmatic way to solve this? Well, a pragmatic way to solve this is that don't send every call to user space of open. For the same file, I mean. Of course, for each file, you will send a call to user space. But let's say you're opening the same file 5 times. So the way it's solved in MacFuse is that there can be a few different types of opens. Opening for reading, opening for writing, opening for reading and writing. So MacFuse differentiates between these 3 types of opens. And open receives these flags so it knows what kind of open it is. So let's say a file is not open at all. I get the first call to open. Okay, I send it to user space. I get a handle back. I get this pointer. I remember this pointer because then I have to give it to reads and all the other calls as context. Now another call comes for read for the same file. I don't have to send it to user space. I just reuse the one I have for read. So we don't have to go into further details. I think this is details enough. But things like these. So it still works and behaves what you expect, but behind the scenes, it's something different that's happening. And so those are some of the, being a closed system. You can't change the system. You can't get it changed. And even if you know that if I had this bit of information in the kernel, in my function, I could deal with it, you can't because not everything in the kernel is exported. It's like all opaque. So you only can use published APIs that Apple exports, which is a good thing. But if you're doing something like this, if you need to do something that's not exported, tough luck. A big challenge is the Finder. File systems for many or most Mac users mean the Finder. If something doesn't behave nicely with the Finder, it doesn't work. And the Finder can be very finicky, very fastidious. And Finder's really honed and whatever for Apple's file systems because that's the only thing that they have and that's the only thing they ship. So things like you mounted something. So the way Fuse works is you have a file system server in user space. You did a mount call. Kernel sent a message to the user space saying, hey, please mount. And now the guy could say, done. But should the kernel wait for the guy to say done? It could. But what if the guy is single-threaded? If the guy is single-threaded, maybe the very next thing that somebody wants to do is to call the guy and say, tell me how many files you have so I can populate this window and do something. So the thing is, for various reasons, we wait for the user space file system to finish mounting asynchronously. So while we are doing that, we actually cannot forward any calls to this person because it may not have initialized. So we hold off all the calls in the kernel. But the mount system call has returned. So as far as the Finder is concerned, something has come up. But then the Finder wants to go and quickly look up this file system and figure out how many files it has, how much free space and whatnot. But remember, we are holding all those calls in the kernel until the guy says, I'm done. Now, you could hold all the calls, but you can't hold really all the calls because what if you're trying to eject it because you decided something went wrong? So ejecting something or unmounting something also needs to know what the status of the file system is. So you at least have to let stat through. But if you let stat through, you don't know what is the status because you haven't talked to the file system guy yet because he hasn't replied to you. So you have to cook up some stat. You have to say, no files, nothing, no space. That's what we are. But if you do that, the Finder could make that call, and the Finder would say, oh, great, empty file system, there's nothing yet. And the Finder would remember that and stick to that thing. And when your file system does come up and when stat actually starts replying with some decent data, it's already too late. So you have to make the Finder happy. You have to do something. I don't want to tell you what we do. It's all good, but details are painful. So we make the Finder happy in more ways than one. User expectations, assumptions, presumptions, belief system, convictions. It's my favorite topic, but I can't talk about it because it's painful for me. Point being that yeah, like I said, people expect things to be a certain way, whether that's correct or not. So if you want to be pedantic, if you want to tell people, no, that's not the way it should be, because that's just not right. And yes, you've been conditioned to believe this, but this is not right. It doesn't work. You want people to use your product or project, then just put up with it. And one has to make the user happy. I mean, it's a very well-known fact. But things like, people are not happy that why is something showing up as a network volume? Why is it not a local? Why are all MacFuse volumes network volumes? They're not network volumes. They don't have a local disk assigned to them because there's only two ways you can do file systems in OS X. You can have a real local disk or not have a real local disk. If you say no real local disk, Finder will show that globe. That globe doesn't make it a network volume. All that means is it's not local. So As far as the kernel is concerned, it is not local because the kernel itself is not reading the disk. That is a local file system. So there are many misconceptions like this, and some of them are very strongly ingrained, and people feel very strongly about them. Finder also has the tendency to, like if the connection breaks, then things die. Finder locks up the GUI, so what to do? The thing is, MacFuse is not the thing that's actually communicating with the remote thing. It's the file system in user space. Like, it could be doing anything it wants. It could be doing a while loop forever if it wants. So what to do? So give people tools and means to interrupt that. Give people tools and means to eject things if they really want to eject things. Other things people do is that people expect that, let's say you're using the SSH file system. You SSH'd into some host. You have some files over there. They're also logging in through the SSH program or AFP or Samba, and they're changing the same files like through MacFuse and outside of MacFuse. And they're saying, it's not refreshing. So I can understand. So the difference here is that MacFuse is not a distributed file system. It's just a way of building file systems. If you have a protocol that knows how to handle concurrent access and whatever, that's orthogonal to MacFuse, and that's a separate issue. So MacFuse itself can't really do much. But like I said, I do want to make people happy and want them to use the product. Let's say somebody really wants the data to be always refreshed and up to date. Every time you open a file, it should show you what's on the server. So the way to do that is OS X does many types of caching. So the way to do that is to disable that caching altogether. But the caching was not really meant to be disabled. So it's kind of tricky to disable that so that things still go through. Another thing is that when you, let's say you're implementing a file system, you're implementing something that streams a file from somewhere. And you don't know, if you're streaming, let's say you don't know what the size of the file is. So what do? So when you read something, the first thing that happens is the kernel will ask you, hey, what's your file size? Then you give it a size and say, OK, give me the data. But if you don't know the size, what will you say? You could say my file size is a gigabyte. What if it's actually more than a gigabyte? Even a gigabyte is not good enough. But let's say you did say a gigabyte and the size was just 10 bytes. What will happen is that the kernel will zero fill the rest. So you will read a gigabyte. That's not what you want. What if you just said 0 bytes? And why does the read not just stop, like start when the provider stops providing the data? Why not just say 0 bytes, don't look at the size, just read as long as the file system is giving you data? Well, that's not how things work, because there's buffer caching, this really complex beast called buffer caching, and it really wants to know the size. So if we want to implement this, that people should be able to say 0 size, and reading stops, writing stops when you're done, then we have to bypass the buffer cache. So from MacFuse to your file system, there needs to be an entirely different software stack for this to work. So we did implement that stack because, like I said, people should be able to do that, and this is a kind of an important thing. So one negative side effect, at least negative in my book, of providing so many features is that not every feature should be enabled every time, because maybe you don't want that. Maybe you want the right size to be present because that's what you're doing. You're not doing a file system like that. So how do you solve that? Well, you provide lots of options. Turn this on, turn this off, turn this on, turn this off. So if you look at the graph of the number of mount time options that we have, it goes something like this. So in the beginning, there were not many. And then it just keeps going up and up and up and up and up. And I call this explosion hell. But at least, like with the previous curve, at least the slope is going down, so it's not increasing at that rate. But that's the reason for. So now that we have a reasonable mechanism in place, you know what MacFuse is, you know what it does, what its features are. I could finally go and do a proc file system. And it was much easier than the previous attempt. And I'll actually show it to you. Actually, I already showed 2 demos here. So here I mounted procfs. What is procfs? Well, so these are all the processes on your system. Look like folders here. You can go down. You can also do by name, and processes that actually have names will look like this. Let's choose something, Safari. Let me actually have a Safari window up. And so I look at Safari. There are things like command line, which contains like the exact command line for this program. There's things like FDs, which actually contains all the open files and sockets and pipes or whatever for this Safari. I could go somewhere, open that file again. Then you go into task. You look at threads. You'll see that this guy has so many threads. You can go to a thread directory. You can go to states. You can go to like state float. Here are all the registers for the threads. I can kind of just, instruction pointer or base pointer. Basically, you can look at all the registers. This is all in real time. So every time you open it, you should get a new value. You can look at things like system time and user time, how long this thing is run. You can see how much memory it's using. You can look at the VM map of this guy. You can see like all the memory that this guy has allocated, all the regions, what it's used for. You can look at his mock port. So basically, you can look at a lot of stuff here. And in fact, it's kind of seamless with respect to the kernel that process 0 is kernel. So if I go and look at the stuff for the kernel, for process 0, I'm actually looking at the kernel. And then we have this thing called system here. You can look at system firmware. It'll tell you all your firmware variables.
That file system is read-only?
This file system is read-only, but you can make it read-write. I just didn't make this one read-write. But it can be like Linux. There's exactly the same thing. Then you have some hardware here. So things like motion sensor readings and light sensor readings. You just open the file and you read it, and every time you read, you get a new value. You have something called displays here. So I have like 2 displays connected. So I'm seeing something for each display. I have display info, which tells me like what the resolution is and whatever. I can do screenshot. Actually, it's giving me a live screenshot of every time you open the file, you actually get a screenshot of your thing. You can actually go and click on it, and well, what do you expect? So you can copy the file. Like you copy it to a desktop, that's the screenshot. You got a screenshot. Copy it again, you got a new screenshot. Copy it from the command line, or copy it from. You can set up a cron job that does that if you're. And then I guess I could go back here. CPUs, we got 2 CPUs. You can look at their data, what they have, how long they've been running. Camera. Huh. So you know what the deal was with the. So in fact, I can also do this. And it takes a picture, and every time you open this file, you get a new picture taken from the eyesight.
Can you export this file system?
Sorry?
Export this file system, and then you got a spy thing.
Yeah. So again, I mean, just copy it somewhere, and you're taking a new file. So if you want some kind of vigilance thing going on, just set up a cron job that copies your file somewhere. Actually, there were a few other things. I might have to go to So let me open a couple of Safari windows. And then so one of the files was, actually I should show you that file first. Go back to the Finder. Yeah, sorry about because I'm not used to looking back and working on the computer. So in by name, Safari, there's this thing called Windows. So you have this file called on screen. So it'll show you a list of, basically it will show you this, which contains that this thing has 2 windows on screen. This thing is the size of the window here. And these are the coordinates, and that's a level at the X, Y, and level. So then we also have this thing called identify. So see what happens when I identify. So for this, I will need the terminal thing. So I will say proc by name, Safari, Windows, identify. So all I'm doing is just opening that file. So it identifies the window that, here they are. So if you have 10 windows, it's going to rotate these like this and identifies. So that's proc file system for you. And that said, no discussion of MacFuse can be complete without some of the canonical MacFuse demos. And these are the ones that I had going here. So we talked about a few types of things you can do with it. So you probably already know that people have written NTFS 3G ports for this thing, so you can read and write to NTFS using MacFuse. People have written SSH GUIs, so you can actually use the SSH file system in a much easier way. I mentioned about using this to bridge the gap between the desktop and the web. So let's say you have something that talks a web service interface to over the web to something else. There are lots of things like that today. Let's look at this thing called DocsFS. So we know Google Docs and spreadsheets is a Google service. So you can edit your documents online and collaborate and share and so forth. But what if you wanted to just look at your Google Docs account and you wanted to just look at them like this was local? So this is your Google Doc account. When I clicked on the thing, it actually logged into my account, retrieved the information, and made it look like they were files on the local volume. And what happens when I click on one of these? Well, it just opens it up in the browser. And what happens when, so there's this thing called converted versions. So I can go in there, I can, Finder is waiting, and I'll have an equivalent set of files here. And if I open it up, it'll open up in Word, and it looks like a Word document. So we have taken, the usual way of doing this would be that you would be reading and writing or exporting and saying save to or downloading or uploading through web forms. And here, you're just dealing with it like you normally would with other stuff. That's local. So that is one example. We have this thing called Picasa file system. Picasa Web is Google's web interface to, like the Picasa web hosting, the photo hosting service. So the idea is that you put your photos up with Google in your Picasa account, and then you can view them online in online albums and whatnot. Example being, I could go to Picasa Web, and you see your albums. I can drill down. I see the photos in that album. I want to upload. I can click on a URL. It'll ask me select a file. But another way to do that would be just open this thing up. And these are all my albums. It's the same view. I can go in here, and I see the same photos. I want to open them. I can just double-click, and it opens up as it would. How to download photos so you don't have to do save as or fill some forms. You just drag it, and that's the download. Now, other operations, lots of operations can just map to this semantics. Like you can say, I want to create a new album. So you could just say, new folder. And that's a new album. I can go back in the web browser, and I can double check. So here's a new album. And then I can go in there. That's the upload. And I go inside here, and the photo is there. So basically, the idea is to let you use these things just as you use everything else. So that's one use of. Some of these are not our demos. Some of these are things that I'm really glad that people have started doing with MacFuse. I'm not showing everything here because you can download them and try them yourself. Here's essentially a semantic file system. So what that means is that you know that Spotlight lets you search, and so does Google Desktop. But one way of looking at the search interface is that I go to this folder called Smarter folder, which has nothing in it. And let's say you're looking for all PDFs on your machine, so the query for that would be PDF. So what if I just tell this guy to go into the folder called PDF, and it'll do a Spotlight search, and we get a file system. And these are the results of the query. And I can just click on these, and they work like, if I copy this whole folder, I would essentially be doing a semantic copy that copy whatever is the result of this query. And like in Spotlight, whatever syntax you can do and or, whatever things you can just use them. And that gives you basically an on-the-fly dynamic file system that the contents of it are based on what you're doing right now. But for all intent and purposes, it works like a real file system. So yeah, and then you already seen proc, and then there's some other examples. One thing I did to help people understand this better was I created a video when we released MacFuse, and it shows you more of, so in case you're interested and you haven't seen, probably you should look at that video. So, and MacFuse lets you do other things too. Another reason why MacFuse, the kernel part is increasing is because we wanted to give people everything that's really possible in a file system. So, you know, OS X had ACLs in Tiger. You can do access control in Tiger. And it's a very good thing. I mean, it's a useful thing if you're in that sort of business or looking for something like that. So MacFuse supports ACLs. And your file system doesn't even have to know about it. So the point is, MacFuse supports extended attributes. So you can have arbitrary key-value pairs, and they will all be forwarded to your file system. The user guy, if the guy says, hey, I want extended attributes, I just don't want to deal with them, can you just store them for me? So the kernel will take a fallback path and store them as Apple double files, and they will be there. You want to use ACLs? ACLs will be there. You want to use KQK event, this thing OS X has, MacFuse has it too. So many of the things that regular OS X file systems have, your user file system will get it for free without even having to know that this thing is there, or you don't have to do anything about it. Before we get to Q&A, I would like to thank all those people who have helped me or who have created some of these demos. They're my friends and they're my team members. And I really, really value their support because, like I said, I go into the zombie mode and people need me. And I'm like, can you talk to me after a week? And they've been very understanding of that. So that thing is just totally invaluable. And also I asked them that it would be great if somebody could do this demo, but you know, somebody. And I don't have to say more, and they volunteer. So it's just great to have support like this. So thank you guys, you know who you are. And with that, we come to the end of this talk, and if people have questions, I'll be happy to answer them. Thank you.
Hi, I think this stuff's great. I'm a big fan of Plan 9's architecture, where everything is a file. But sometimes I feel like people like you and me are freaks, and no one else gets this. And I'm curious, outside of your team, where maybe, I don't know whether people do it because they just like you or because they really buy into it, how do your fellow Google developers feel about this model, where basically the file system is the object interface? And also, now that it's written, how does Apple feel about it? Do they actually see the light now that you've actually implemented this?
Good questions, but difficult questions. I mean, as far as Apple is concerned, this is under a free license, so if Apple thinks this is great and if Apple wants to use it, it's open source.
I'm curious whether you've spoken to them about this.
I have not really spoken to them. I do know that based on some of the engineers I've talked to, I ran into them, that they really like it, but that could be just the engineers. So I can answer for the people that I've talked to. They thought it was a great idea because they're like-minded people. But how does Apple as a company feel? I can't answer that. I don't know. As far as Google's concerned, we have a lot of Mac users at Google. So they like using it, that's for sure. And SHFS is really useful. As for where this is headed, will this play a role here or anywhere else? Can't say. I mean,
well, how about beyond the the obvious things where you have what you would consider a traditional file system like SSHFS, which just exports real files on another machine securely. I guess I'm curious about using it for things like what you showed with Picasa Web, things that you don't traditionally think of as a file system, but this and things like Plan 9 are able to export as file servers. Do you think that other developers at Google get that idea? Do they see value in it, or are they just basically developing standard libraries and doing things through like XML RPC or whatever? No,
so I mean I can't talk about Google's plans either way, but I can say that first of all, this thing is very new. So even if people here or outside think that this is really great and this should be in products, we just released it in January. So it's a file system. It's destabilizing by nature. So it'll take a while to bake. And the other thing is that whether at Google or elsewhere, lots of these products have been out for a really long, long time. So changes like this anywhere, they don't happen overnight.
But as you pointed out earlier, there are this idea has been around for a long time, and it just doesn't seem to have really caught on. And I'm just curious whether is that because of the systems that it's been developed in haven't caught on? Is OS X a chance to actually make this something that's feasible and used?
I certainly hope. I certainly hope that, or I think that we have at least as good a chance, if not a better chance, than the previous systems to do it on OS X, simply because I think the community is very innovative, and the tools, like the default tools, are quite powerful. So. Yeah. Just if you want to make something very visually appealing to get your point across and convince people that, hey, look, this can be quite cool, is by nature it's a little easier on OS X if nothing else. And I'm seeing some of that both inside and outside of Google. Like people are excited about it.
That's, I guess, what I was getting at. I was curious whether people are actually, whether you'd have to do much evangelization or whether just showing them these demos is enough to go, oh yeah, okay, I get that.
Yeah, I think for the most part, people see the demos and they're quite happy and excited. The thing with Plan 9 and all is like Plan 9 is arguably like even a better way of doing this because that's the system from the ground up, and file server in the kernel and user space doesn't matter. Just you can do whatever you want. But the thing is, we're not running Plan 9 for whatever reason. So yes, and that's why I make it a point to make it clear that this is nothing new. The execution might be new, and whether that succeeds in the 100th attempt or the 200th attempt, that's to be seen.
Thanks a lot.
Mm-hmm. Thank you.
What kind of performance hit do you take? For instance, if you used a MacFuse file system as an interposer, what kind of slowdown do you think you would see?
Yeah, actually, that's a good question. I should have included in the user perception kind of thing. So it's a multifaceted question with a multifaceted answer. So the question is, what kind of performance for disk-based file systems? What kind of performance for something that's coming across the network? What kind of performance for something that, like procfs that you're cooking up? So if you're doing a real disk-based file system, like let's say you're doing NTFS, then, so there's MacFuse overhead by itself, and that's actually pretty close to the theoretical, which is you're doing at least twice the number of system calls, because you're going back to user space and then you're coming back in, so you're doing quite a lot of system calls. So one might expect it to be at least twice as expensive from that standpoint. So there's a very good way to measure it, which is use the loopback file system. So there's a loopback file system that mounts your root directory onto somewhere else. And then the only overhead is you're going to user space, and then you're making the actual call. So if you open the user space file system, it's just doing open and coming back. So with that, it's typically 1.6x to 1.8x, which isn't bad at all.
That's pretty good.
And with network file systems, the network really is the bottleneck most of the time. Like with SSH file system, my personal experience on OS X has been that it either beats SCP, or it does at least as good as SCP. Because we're doing buffer caching and all that, so if you're doing interactive work, then you're definitely much better with that than SCP or something else. So on that front, I'm actually quite pleased with the results. And the performance should not be the issue. Like people shouldn't really worry about that. People should just think of like what neat things could be done. If you're writing disk-based file system, let's say you're doing NTFS, and throughput, like raw throughput, megabytes per second or gigabyte per second is an issue, then there's a bigger problem, because MacFuse is not the only thing in question here. If you're reading and writing to a raw disk, OS X doesn't have a disk block cache the same way that Linux does. So if you're opening, like let's say dev disk, and you're reading and writing from it, then you're much better off doing that on Linux than on OS X, and that's just an architectural difference. So that alone will kill you. So there are solutions, though. You could implement your own cache, whether in user space or in the kernel. So we had a lot of grumbling from the NTFS people who were using NTFS that, hey, this sucks, it crawls, it's just so slow. Who is at fault here, NTFS or Fuse or MacFuse, or what is going on? So well, what is going on is that NTFS, the program, is opening the raw disk, is doing a lot of random I/O, none of which is cached. So what to do? It is hitting the disk every time, and it's seeking every time too, because it's doing a lot of random seeks and stuff. So essentially the worst case for disk-based I/O. So one way to solve that, so as an experiment, I wrote a small file system that takes a disk, like a dev disk, and mounts it as a file, and which is essentially the way Linux does it inside the kernel. But if you mount it as a file, then you get the benefit of the buffer cache that is there for files. So that sped up, for certain workloads, it sped up performance like 20x for NTFS. So essentially, that shows that that's most of the reason.
Okay, thanks.
Thank you. All right, so no more questions, and if people do want to ask offline, please feel free. Thanks again for taking time to come here.